Hey, welcome back. This is 14.8 on Jacobians. Um, so here we go. And a Jacobian is basically a factor that accounts for U substitution. So you've kind of already seen it with regards to the converting to polar coordinates. So if you have some integral over some region of f of x comma y d y dx, you could do a polar conversion here and get a new integral over a new region of f of r cosine theta comma r sine theta, and then r dr d theta, right? That r factor right here is a Jacobian, and that's what we're kind of trying to find. We want like a formula for that thing that is a little easier to get at without having to resort to some weird geometrical argument. Okay, and that's what we're gonna get here. So the way I've started to think about this is thanks to this guy from Cora. Was Mark Eichenlaub. He's a PhD in the University of Maryland, does physics education research. And anyways, he begins with in one dimension. So recall the U sub, and also recall kind of more of a trig sub idea. So you kind of already have two substitution ideas from Calc 1 and Calc 2. You could do a substitution. So let's say I have sine of x squared, and I'm trying to integrate this thing. It's the same example that Mark uses in his article there. You could try the sub it for x squared. Of course, it's not going to work. You get du equals 2x dx, and then dx is going to be du over 2x. You could also do what's more of a trig sub. So instead, you will say let x equal something, some function of u, right? So let x equal the square root of u, and then dx will equal 1 all over 2 square root u times du. Okay. That thing right here, this factor here, is basically a Jacobian. This is a Jacobian. And what it's doing is accounting, as Mark over there says, it accounts for kind of a warping or let's see that he has some nice pictures. Okay, so you're starting with this kind of purple rectangle, and then when you do the U sub, it's warping that rectangle. Okay, and that factor there is how much the warp is, and that's the Jacobian. Okay. Okay, so that's one dimension. We want to kind of take this now into two dimensions, right? So in one dimension, you're basically stretching your change in x, okay, and getting a new sort of change in x in terms of u. Now we're going to be warping an area instead of maybe just an interval on the number line, right? So now we have a more complicated situation, and let's take a kind of a look at that. So let me set this up as a new section called change of variables, but it's basically just kind of a substitution, a U sub, but in the trig version, the trig substitution direction. Okay, so it's going to seem a little backwards because of that, because it's not direct like we're used to. And the book is going to introduce this T transformation. So in the picture that's kind of going on with regards to the second substitution, you start with a change in x, which is probably something underneath the curve, like this right here, and then you're going to do a transformation and you'll get sort of a new change in x, but it will be this du thing, and it will be stretched, right? And we want to know kind of in terms of u, how much is that stretch, right? Oh, geez, my cat is flipping out. He does this. Hold on. My God. Right, so the transformation is going to be some t of u, and that of course will equal x. Okay, in this case it's the square root of u, which will equal, x. Okay. Right, so you'll see the same transformation now, except it's in terms of two variables, and so let me write out that transformation. TUV, and that equals x comma y, where in particular g, u is going to be some, t of u is going to be, well, x will equal g of uv, and y will equal some other function, h of uv. Okay. So you're going to have two formulas, one for x and one for y. And when you're doing your homework, you're kind of going to be jumping back and forth between the two versions, but you'll have some picture in the UV plane, and that transformation will turn it into a picture in the XY plane. Okay, so it's kind of the same idea here, but you just have a single variable, and you're going from U to X. Okay. Okay. So the rectangular picture over here, we have something like this in the XY plane. Have points M, Q, P, and N. And then over here we have our picture in the UV plane, which hopefully is much simpler. And the coordinates on this thing, we're going to take this bottom point to be U comma V. And then this point will be U plus some change in U comma V. And then this point here will be u comma v plus change in v. And then this other point here will be u plus change in u comma v plus change in v. All right. So we kind of want to run all of these through that t function, and develop some formulas to do this transformation. And we essentially want a formula, a new formula for this dy dx part in our old integral. Okay, just like in the trig subby type version of our substitution, we're after kind of a new formula for dx, right? You transform dx into this guy right here, some factor, the Jacobian times du. Okay. Alrighty then. So I want to transform delta x, delta y, which I consider to be delta a. And in order to do that, I can just basically figure out the magnitude of the cross product of the vectors mn and mq. So if you remember from way back when, I kind of, even on the test, how do you find the area of the trapezoid using a cross product, right? So it's that idea. And this thing, from this, we're going to be able to get the Jacobian. So this is going to give us part of the Jacobian, but it'll give us what we're after. Okay, so I have to figure out what that thing is. And what I'm going to do is rewrite M, Q, and N kind of in terms of the G and H functions above. Okay, so M is going to be G of, and so I'm going to say it's this point right here. Okay, so it's G of U comma V. Sorry, I went to the wrong color there. Comma H of U comma V. And then the other points Q, I'm going to say that's the U comma V plus change in V. U comma V plus change in V right here. That's going to be my Q. I'm going to make this point my, I believe I don't even really need it because I'm just looking for vectors. Okay, but if I did need it, well, I don't think I'm going to need it. I'm just going to need n. Okay, so I'm going to make this n. Okay, so I just need those points for the vectors. So anyways, then Q, like I said, is going to be G of U comma V plus change in V, comma H of U comma V plus change in V. And then N is going to be G of U plus change in U, comma V, comma H of U plus change in U, comma V. All right. So I can form my vectors based off those. I need M, N, and MQ. So Mn, you're just taking differences of components at this point. Starting at M and ending at N. So it's going to be G of U plus change in U, comma V, minus G of U, comma V, and then the same thing with the H. And then MQ is going to be the same spiel, but now I have G of U, comma V plus change in V minus G of UV, comma H of U, comma V plus change in V minus H of U V. And then the terms in these guys look suspiciously a lot like the difference quotient terms from partial derivatives, right? And truthfully, that's kind of the way we're going to approach it. So if the delta U is small enough, we can kind of approximate that thing, right? So we could say the partial derivative of G with respect to U is approximately the same thing as G of U plus change in U, comma V, minus G of U, comma V, all over change in U, and then just multiply both sides by change in U, and we could rewrite this vector Mn as the partial derivative of G with respect to U times change in U, and then again we could rewrite the second component as the partial derivative of H with respect to U times change in U. And then for MQ, of course, we could do the partial derivative now with respect to V times change in V, and then H partial derivative with respect to V times change in V. And then getting the cross product is easy. So this cross product thing, Mn cross MQ, is just going to be, GU change in U, HU change in u, and then gv, change in v, hv, change in v, 0, 0. And then that will be 0, comma, 0, comma, gu, change in u, hv, change in v, minus gv, change in v, hu, change in u. And then you could factor out the change in u, change in v, and kind of look at that as a constant, but we need the magnitude of this cross product, right? So ultimately then I'm going to have to get a magnitude on this, and so that will equal the square root of all that junk squared, right? So gu, change in u, hv, change in v, minus gv, change in v, hu, change in u, squared. So you again factor, I mean, you get rid of the square, but it'll be g u h v minus g v h u times change in u, change in v, and this part here is the Jacobian. Okay. Okay, so getting back to kind of the where the book is, then what do we have? Let me rewrite what we have. We have change in x, change in y equals our delta a, which we're saying is basically the magnitude of that cross product. And let me write it more like how the book has it. This will be then, because of the square root and stuff, it's the absolute value of this. The way we're going to write it is you have a function of x and a function of y, right? So the function of x was the g. This is our x function, and h is our y function. Okay, so basically you have the partial derivative of x with respect to u times the partial derivative of y with respect to v minus the partial derivative of x with respect to v times the partial derivative of y with respect to u. Okay, and this junk is the Jacobian. And the way they usually write it in the book, let me just give you a heads up, which is kind of weird. It's basically the partial derivative of this xy thing with respect to u and v. It's kind of just like another way of writing a partial derivative, but now you have multiple variables. Okay. All right, so that's kind of it. The rest of it is just a lot of computations and going back and forth between these g and h functions and the u and v functions and the x and y functions or whatever. And yeah, they give you a formula for the Jacobian in terms of, I gotta get my cat up here. He's having such a hard time today. Right, so they give you a formula for the Jacobian in terms of determinants. So the Jacobian is basically the partial derivative of x with respect to u times the partial derivative of x with respect to v times, and then we had the partial derivative of y with respect to u and the partial derivative of x with respect to v. So again, you know, if you just multiply on the diagonals there, you're going to get what I had written before. But they think this is a clever way of memorizing it. I don't know if that's, oh, wait a second. It's dy here. But in my opinion, it's just kind of adding insult to injury at this point. But all right, whatever. Then you have dx dv dy But you see, it's just the Jacobian. It's just that thing. All right. Let's kind of, if you apply this process to the polar idea, you'll get that factor of r as your Jacobian, and I believe they show that to you in the book. I'm not gonna, yeah. So example one. I mean, we could do that, but you can also read it, hopefully. So you see they have these sort of substitutions in terms of r's and thetas, and then they find the Jacobian, and it turns out just to be r from r dr d theta. So, wow, surprise, surprise. I don't find the examples very helpful with regards to the homework. The homework seems to just kind of be created by a different human altogether. And you kind of have two choices here now with the way you do your homework. You can kind of create, I'm trying to get this stupid thing to pull down and it's not letting me for whatever reason. There it goes. You could, so what is it talking about? You could try to create a method for each individual kind of problem. So you'll have like 5 methods and you're going to spend your time trying to optimize each method. Or you can basically try to just create one method that always works. And that's kind of the approach I take. I just use one method, it always works, but sometimes it's kind of a lot of work. Okay. But in my opinion, it's easier to remember than having to go through multiple methods that have been randomly optimized based off of a couple problems that you may never see again. So I believe my methodology is kind of, developed so that I can handle the actual problems, but it'll also kind of handle these preliminary exercises, which in my opinion are kind of just silly to an extent. But okay, so let's take a look at what we're up against here. Let's look at number 2. Find the Jacobian for the indicated change of variables. So I have x equals 5u minus v, and then y equals 6u plus 2v. So this is pretty simple. You're just, your Jacobian is going to be 5, -1. That's the partial derivative of x with respect to u, partial derivative of x with respect to v. Likewise for y, so it'd be 6 and 2. This will be 10 minus -6, and that's 16. A word to the wise. In the book, when you're reading it, it kind of looks like the Jacobian has an absolute value around it, like here. And that's true, because the Jacobian is, finding the Jacobian, you need the magnitude of it, and the magnitude is going to be positive, right? So yeah, it has an absolute value around it when you put it into the formula, but for the Jacobian itself is the thing inside the absolute value. Okay, so see number 1, it can be negative. Okay, it's just when you go to put it in your integral, it's always going to be positive. All right, so anyways, let's take a look at number 3, where we're sketching this thing out. So number 3, and I'm not an expert in Jacobians by any stretch of the imagination, so I rarely use them. And okay, so x equals 3u plus 2v, y equals 3v. We want to figure out what this thing looks like in the uv plane, and they give you a picture in the xy plane. The book, if they had an example like this, would probably just tell you to convert the coordinates using those formulas. But even to do that, you're going to have to rewrite everything in terms of x and y. So you're going to need a formula for u in terms of x and y, and a formula for v in terms of x and y. My approach is to find the formulas for the equations in terms of x and y, and then you'll have you could do substitutions. So what this is the xy plane. I want to put it into the uv plane. Okay, so I'm going to get formulas for each of these curves. So I need to take the points and do point slope form, all that jazz. So I'm going to go, yeah. Was there a quick way to do the ax plus by form? Probably not. So anyways, the slope is going to be 3 halves, and then y minus 0 equals 3 halves x. And that would be the first line. Another line 0, 0 to 3, 0. That's just going to be the line y equals 0. So sometimes you just look at it and know. And then the third line 2, 3 to 3, 0. And so that's going to be, the slope is negative 3 all over 1. So negative 3. And then I'm going to use this point for, of course, the formula I'm using y2 minus y minus y1 equals m times x minus x1. That's a formula I'm kind of using for this junk. It's probably better to put everything in terms of x plus y if possible. So in those cases, it's going to be the formula. You could just rearrange it, right, and have y minus y1 equals mx minus mx1. So you would get mx plus y equals minus mx1 plus y1, which doesn't look very helpful, but that's kind of the form you're usually going to be going after. So anyways, we have y minus 0 equals negative 3x plus 0. Okay. And so to get the equations in terms of u's and v's, you could literally just do substitutions now. So this first guy is the same as 3v equals 3 halves times x, which is 3u plus 2v. So I get 3v equals 9 halves u plus 3v. So the 3v's will cancel. You get 9 halves u equals 0. So u equals 0 is one line. Maybe let's circle that guy in red. Then for this curve, you would have 3v equals 0. In other words, v equals 0 for another curve. And then finally for this guy, you have y is 3v equals negative 3 times 3u plus 2v. 3v is negative 9u minus 6v. So I have, you could solve for v, add 6 to the other side, you get 9v equals negative 9u. In other words, v equals negative u. Okay, so those are our 3 lines. I'm just doing, I figure out the equations of the lines in the xy plane, and then I do substitutions, and that works. Right? It's not the prettiest thing in the universe, but it works. And I'm sure there's a quicker, faster way to do it. Like I said, you could probably just convert the coordinates, the 3 coordinates they give you, but that's not always going to work, so I don't bother. So anyways, now in the UV plane, plotting those things out, u equals 0 is the v-axis, v equals 0 is the u-axis, and v equals negative u is just the diagonal going downwards. So that's not going to work. So I must have screwed up something, because that's not going to work, man. V equals negative u is this line, so I screwed something up. Let's see what I screwed up. Hold on. I see it. So no, I don't see it. Okay, I found it. It's right here on this equation. So this guy should be, instead, y minus 0 equals negative 3 times x minus 3. There it is. So this will be y equals negative 3x plus 9, and then do your substitutions. So you got 3v equals negative 3 times 3u plus 2v plus 9. So what are we getting? 3v equals negative 9u minus 6v plus 9. Move this v over, so you get 9v equals negative 9u plus 9. Divide by 9v equals negative u plus 1. So that's right. So that's basically y-intercept, or in this case v-intercept at 1, slope down 1 over 1, and that would be our picture then. Okay, I think that was our picture. It seems like it's this guy. I don't know. Yeah, so they're kind of tedious. Let's look at number 4, just to kind of give you a flavor for it. Right, so number 4, look at that thing. I mean, you got to figure out these functions, and they give you fractions in there, so it's just kind of annoying, you know, the way they've done these problems. But there's 4 lines there. You might as well get the, yeah, sure. Let's get the lines first, and then we'll do substitutions with the equations given. So 0, 1, 2, 1, 2. So the slope, 2 minus 1 is 1, all over 1 minus 0 is 1, so the slope is 1. And then you get y minus 1 equals 1 times x. So y will equal x plus 1. And then let's get another guy. The bottom line here from 1/2, 1/2 to 3/2, 3/2. And it's clear to me that that's just the equation y equals x. And then, may not be clear to you, but you could go through the, get the slope and do the point slope formula to get there if you need to. Anyways, the other points, 1 or 0, comma 1 to 1/2, comma 1/2. So the slope there, 1/2 minus 1 is minus 1/2. All over 1/2 minus 0 is 1/2, so that's negative 1. So y minus 1 will equal negative 1 times x minus 0. So y would equal negative x plus 1. Then the other guy, we have 1 comma 2 to 3/2, comma 3/2. So the slope would be 3/2 minus 4/2, which is negative 1/2, all over 3/2 minus 2/2, which is 1/2, so slope of negative 1 again. This time I'm going to go y minus 2 equals negative x minus 1. I'm rewriting that. Y minus 2 equals negative x plus 1. Y equals negative x, I guess it's plus 3. Then we can start doing our subs. So x is 1/2 times u plus v. Y is 1/2 times u minus v. So for our first equation, y equals x plus 1. You may want to just rewrite it as x minus y equals negative 1. Because x minus y, if you were to subtract these things, you can kind of see how that's going to work out. It's going to be 1/2 u minus 1/2 u is 0, and then 1/2 v minus negative 1/2 v is going to be v, right? So x minus y is just going to end up being v, and that'll equal negative 1. Okay. Let's see, the other one was y equals x. So you could rewrite that as x minus y equals 0. In other words, v equals 0. Then you could try y equals negative x plus 1. You could rewrite that as x plus y equals 1, right? So if you add x plus y in this kind of column-wise fashion, now the v part is going to cancel, and you just get 1/2 u plus 1/2 u, which is u. And then finally, y equals negative x plus 3. You could rewrite that as x plus y equals 3. And again, x plus y is just u. Okay, so we have in the uv plane, u and then v. U is going from u equals 1 to u equals 3. And then v is going from 0, the u-axis, to v equals negative 1. So I need some room down here, sorry. Negative 1, and it's this region here. Okay, so yeah. Okay, so yeah. Finally, number 5, we're tasked with actually doing one of these integrals. So we want to figure out the integral over this region R of 4 times x squared plus y squared dA. And they give you the substitutions. Eventually you have to figure out the substitutions, like in problems 9, 10, 11, and yeah, usually your forms for your substitutions, you're going to let like x plus y equals u, and then x minus y equals v, or some variation on that. But anyways, in the beginning they kind of force you to use a particular substitution. So anyways, number 5, in order to get kind of your bounds on your integral, you're going to have to figure out, do sort of this conversion that we've been doing up here. Because these v equals negative 1, v equals 0, those are going to be the limits on your integrals, on your new integral. So you have to go through that process anyways. So for our x, y picture, I have all these lines. And you may be able to just kind of guesstimate what those lines are because they've been made so simply. So for this first line I see here, that has a slope of up 1 over 1, right? The slope is 1. And then you have y equals slope times x plus the intersect. And the intersect is just at 1. Y equals 1, okay? Again, I'm going to rewrite it as x minus y equals negative 1. Because if you look at the u subs here, and then y equals 1/2 times u minus v, you have that kind of that same phenomena going. If you add x plus y, you're going to get 1/2 u plus 1/2 u, which is u. If you subtract u and y, you're going to get x minus y equals v. Okay, so I'm going to try to put things into those terms because now I will have my limits on my integrals. So u will go from, of course, or sorry, v will go from negative 1 to so this other curve, right? So you want to pair together the parallel curves. That other curve 2 has slope 1 as well. They have both the same slope. And then you'll have y equals x minus 1 because the y-intercept that time is negative 1. Right, which you could rewrite as x minus y equals 1. In other words, v equals 1. So for the other two lines, number 3 here, the slope is clearly negative 1 and its intercept is at negative 1 as well. So in this case you get x plus y equals negative 1. In other words, u equals negative 1. And then you have line 4, which also has a slope negative 1, but then y-intercept is going to be at plus 1. In other words, x plus y equals 1, so u equals 1. Okay, you're also going to need your Jacobian. So the Jacobian will come from your substitutions here. Okay, so my Jacobian is going to be partial of x with respect to u is 1/2, with respect to v will be 1/2 if you just distribute the 1/2. Then the y portion, it'll be 1/2 and then negative 1/2. That'll equal negative 1/4 minus 1/4, which will be negative 2/4, which will be 1/2. And then I have to take the absolute value of that. Okay, so the absolute value of that is positive 1/2. So the Jacobian is positive 1/2. I still need to kind of convert this material. So there's just so much to do, it's not even funny. So what do I have? 4 times x squared plus y squared, which isn't as bad as it seems. Let me look to the right here to get my x and y. So x squared is going to be u squared plus 2uv plus v squared all over 4. Y squared is u squared minus 2uv plus v squared all over 4. And now I can reduce that. Factor out the 1/4. I just get u squared plus u squared is 2u squared. The 2uv's will cancel. And then I get plus 2v squared in my integral. So now I'm ready. Believe it or not. Oh, yeah. So what do you have then? You have 2u squared plus 2v squared times the Jacobian of 1/2 times, you could go du or dv, I don't really care. Let's go du dv. And then u is going from negative 1 to 1. V is also doing the same thing. And you can multiply by the 1/2 and it'll get rid of all the constants. So this part will be u squared plus v squared. And then integrate with respect to u, so that would be u cubed over 3 plus uv squared, evaluated from negative 1 to 1 of dv. That's going to be 1 all over 3 plus v squared minus negative 1 all over 3 minus v squared dv. And that will equal 1/3 plus 1/3 is 2/3. V squared plus v squared is 2v squares. I need to integrate that with respect to v. So I get 2/3 v plus 2v cubed over 3 from negative 1 to 1. And that's going to be 2/3 plus 2/3 minus 2/3 minus 2/3 minus 2/3 minus 2/3. So it just looks like it's 4 times 2/3, which is 8/3. Okay, which is the answer. Okay, so quite annoying. And that's pretty much the program I follow when I do these integrals. It becomes a little easier when they're not forcing these substitutions on you, because then you're not going to have to do all this weird converting. So it's a little bit more difficult in what they're doing. Let's look at one more of these 7 before we kind of, well, I guess maybe we should look at 8. We'll do a couple more. You could sort of skip over problems if you don't want to do it, but just be aware the video quiz is coming up eventually. Actually, I think I'll make the video quiz number 10 down there. But I want to do these 2 and then do number 10, which will be the video quiz, and then I'll be done. Okay? Okay. So let's look at number 7. I have the double integral of r 9 times x plus y times e to the x minus y dA. Our subs are kind of given, but you know, here is my x and y. I have 3 lines that I'm worried about, and I got to do their subs. And translate this into the XY plane. Transforming a triangle, you'll learn through we did that one example so you're not always going to transform it into a nice little square. So like in number 3, we transformed the XY into UV, but it's a triangle. And on the limits on the integral, you're going to have an expression in terms of U. So you're going to integrate from like v equals 0 to v equals negative u plus 1, and then u equals 0 to 1. Okay, so you're not always going to get these nice numerical limits on your integral like we did in the previous problem. Okay, so just a fair warning. It doesn't happen very much. As a matter of fact, I think this is the only problem it happens in, but let's take a look. Right, so I need these formulas. So the first line, again, let me sort of number the lines. The first line is that horizontal line through 1. Clearly, that's just y equals 0. Okay. The second line is has a negative slope. Y equals negative x plus 0. And then the third line, y will equal just positive x. Okay, so transforming these guys using this x and y transformation above, we have 1/2 u minus 1/2 v equals 0. So u will equal v, and we want v equals u. V is kind of like the y variable. And then here we kind of have x plus y equals 0. And again, you can play this game where you just add these together. X plus y equals u. So we have u equals 0. And then here, this is x minus y equals 0. So x minus y, if you kind of play the same game, that will equal just v. Okay, so v will equal 0. And so in the uv plane, a little bit careful of what I'm integrating, I have v, so that's not right, is it? Seems like it's right, but it wouldn't be right. What do we have? We have u equals v, and then we have these two curves, which doesn't give me a read. I screwed up again somewhere. Hold on. It's not y equals 0. Sorry. It's y equals 1. Sorry. Oh, plus 1. And then we want v equals something, right? So we want v equals u minus 1. Okay, that'll help. Let's make sure that's right before I decide to move on again. So let's see, I'm going to move the 1. No, and it's not right because you have to multiply by 2. So this, so it just screws it all up, right? So I'd have to multiply this thing by 2 on both sides to get rid of the fractions. So I'd end up with a 2 here. And then I want to solve for v. So move the v over. And, well, no, you move the 2 over. V is u minus 2. Okay, so I think that'll work. Okay, so looking at this, 1, 2, u is going like this, and this will be the region we're integrating over. So in our new double integral, and I still need my Jacobian, and I still need to translate the 9x plus y thingamajig, which won't be so hard. So the Jacobian looks like it's just the same Jacobian as last time. It'll be 1/2, 1/2, 1/2, negative 1/2, which will be negative 1/4 minus 1/4, which will be negative 2/4, which is negative 1/2. Absolute value of that will be 1/2. So my Jacobian is 1/2. What else do I need? I need to rewrite this expression, and we kind of already sort of did that. It'll be u for x plus y is just u, and then there's a 9, of course. And then e to the x minus y is v, and then you got your 1/2 du dv, however you want to cut it. So it's 9u e to the v, and then I'm integrating from this curve to this curve. So that's with a v, right? V equals u minus 2 to v equals 0. And then I'm going point to point on the u-axis. So I'm going from u equals 0 to u equals this point, the intersection. So that's going to be u equals 0 to u equals 1. And I forgot my Jacobian is in there as well, so I just put 9 over 2, if you don't mind. Alrighty then, let's go at it. I'm going to factor out the 9/2. I have the integral of u e to the v. There should be a du here. dv du. So that will be a 9/2 integral of, with respect to v, it's just u e to the v. And then we have to integrate this from u minus 2 to 0 du. So it would be 9/2 integral of u e to the u minus 2 minus u e to the 0, which would just be a 1 du. And it looks like I'm going to have to do by parts on that, on this part. Okay, first I'm going to rewrite it though. Well, no, let's not even bother. We'll just do by parts on that. So I'm going to do p's and q's, p dq. So from Liate, you have to do the algebraic first, and then e to the u minus 2. Q will be e to the u minus 2, and then dp, of course, is du. I'll just write du. And then we'll have 9/2 times u e to the u minus 2 minus the integral of e to the u minus 2 minus this other guy is u squared over 2, evaluated from 0 to whatever, 1. So this will be 9/2 integral u, 9/2 times the terms u e to the u negative minus 2 minus the integral of e to the u minus 2 is e to the u minus 2, and then minus u squared all over 2, and then we have to evaluate from 0 to 1. So that'd be 9/2. Putting in 1, you get 1 e to the negative 1, and then minus e to the negative 1, and then minus, putting a 1 in there, 1/2, and then minus parentheses 0, minus e to the negative 2 minus 0, and some cancellations, of course, times negative 1/2 plus, and I must have made a mistake somewhere, plus e to the, so it's 9/2 times everything, right? The heck did I did it backwards. Yeah. I put the antiderivative in backwards. Sorry. So I should have put in 0 first. So it should be just 0 minus this thing. Oops. I mean v. E to the, it should be just 1. U times 1. So this would be plus, and this would be minus. So this is going to be minus, and then I guess plus. And this will be plus. This will be then minus, and then plus. This is plus, this is plus, this is plus, and is that it? It's still not right. I still did something silly. So this would be e to the, rather, something closer, minus e to the negative 2, which is still not right. So let me pause the video and see what else I did wrong. Oh, I see. The outer bound's to 2 because it's right. It's right here. This point is 2, 0. So the upper limit was wrong. That should be a 2. And then going down here, this will be a 2. And then I should probably just erase all this baloney. Honestly, I used to do all my lectures twice. I would do like a preparation lecture and then the actual lecture. And I've kind of gotten away from that because like nobody else on the planet does it. You get no reward for doing it. So all you do is get punished because you're spending all your time preparing lectures and you're not doing all the things that the administration wants you to do. So no offense to them. But as a result, they're forcing me to conform to their rules. Now you have tons of mistakes in your lectures because they're not giving me enough time to prepare my lectures. So if you want to blame anybody, blame the administration. Anyways, plugging in 2, what do we get? So we get negative 2 and then e to the 2 minus 2 is just negative 2, plus e to the 2 minus 2 is just 1, and then plus 4 over 2 is 2, then minus 0 plus e to the negative 2 plus 0, and of course that's just 9 halves times 1 minus e to the negative 2. Okay, all right, so I want to do that one. Let's do number 8. So our integral y sine of xy dA, and have x equals u over v, and then y equals v. So the region that's drawn out, this time they finally give you the formulas here that you want. We have some nice formulas, right? So one thing you can notice is if you kind of play around with these two formulas that are given, x equals u over y, if you just substitute in for v, and then that will give you xy equals u. So you have u equals xy and you have v equals y. So for your bounds on your integral, your limits on your integral, if you look at the picture, you're going from xy equals 1 to xy equals 9. So basically you're going from u equals 1 to u equals 9. And then for the other guy, you're going from v equals 1 to v equals 9. Okay. For your Jacobian, then you're going to have, the derivative of x with respect to u is 1 over v. The derivative of x with respect to v is negative 1 over u over v squared. And then the derivative of y with respect to u is just 0. The derivative of y with respect to v is 1. So the Jacobian is going to be 1 over v. And then translating this y sine of xy, the integrand, you could replace y with v and then xy with u over v. So you get this expression, and pretty much that's all you need for this integral to pan out. So let me just set it up. I won't do the integral for you. You could do the integral yourself because it's pretty simple. But anyways, I'm going to go from v equals 1 to 9, and then u equals 1 to 9. And then we have inside here v sine of u all over v, Oh, wait a second. XY is just u, right? So we could do, I don't know why I wrote u over v. XY is just u. And then we have our Jacobian is 1 over v, and then you have dv du. So that integral simplifies really nicely into sine of u dv du. And I'll leave that integral to u so we can carry on to our video quiz. All right. So our video quiz is number 10 here in WebAssign. Let me mark that in my notes. So this is video quiz set, I think it's number 9, maybe even. No, it's number 8. This is the 4th question in video quiz set number 8. And I can't get, there's 2 pieces of paper stuck together. I can't get them apart. Okay, there we go. So this is the 3rd one, 14.8, and it's problem number 10 in WebAssign. Okay, here we go. Video quiz, video quiz, video quiz. All right, so let's take a look. I have f of x comma y equals x plus y times e to the x minus y, and the region given is 1, 2, 3, 4, 0, 1, 2, 3, 4, 4, then 6, 2, and then 2, 2. Okay, so we have this kind of box here, or diamond, or whatever you want to call it. I need to figure out now these transformation formulas that they're always been giving to us. And what I have to do for me personally is just go through and get the equations for all of those lines, and then I can kind of see what the transformation. Usually it's going to be like x plus y, u is x plus y times a half, or u is, you know, or sorry, how do they go? X is, or no, I want the u formula. So u is, well, you'll see. Okay. All right. So let me mark down what these points are. This is 4, 0. This is 6, 2. This is 2, 2. And then this guy is 4, 4. All right, so let's get this line first. So it'd be 2, 2 to 4, 0. And so I have 0 minus 2. Minus 2 all over 4 minus 2, which is 2, so negative 1. So y minus 0 equals negative x minus 4. So y equals negative x plus 4. And I always want like x plus y or y plus x to be my, you know, I want u to equal x plus y and v to equal x minus y, or some variation on that. Sometimes I think one of the problems I had u equals x minus 2y, you know, something like that. So here I'm going to put x plus y equals 4. Let's get line 2, and I'm going to let u or v equal x plus y. So I'll probably let u equal x plus y, right? So on the next point, I got 4, 4 to 6, 2. All right, so the slope will be 2 minus 4 all over 6 minus 4. So I got negative 2 all over 2, which again, same slope, right? So I'll have y minus 4 equals negative x minus 4. Y minus 4 equals negative x plus 4. So y will equal negative x plus 8. So x plus y equals 8. Okay, so in other words, we're going to have u going from 4 to 8. Okay. Okay, and let's get to another line. So make this line 3 here. That's clearly just y equals x, 2, 2 to 4, 4. So y equals x, and so I'm going to make x minus y equals 0. That the v will be my x minus y. Okay, and of course here v will start at 0, and then this other point, this other line, 4, 0 to 6, 2. You can kind of see it's going to be y equals x minus 4, but it's better safe than sorry in my opinion. You get 2 all over 2, which of course is 1 again, and then you get y minus 0 equals x minus 4, certainly. So you're going to get x minus y equals 4. So you're going from v equals 0 to v equals 4. I need my equations for u and v. So anyways, I need equations for x and y so I can get my Jacobian. So if x plus y equals u, then x equals u minus y. We have x minus y equals v. So y will equal x minus v, and so x equals u minus x plus v. So I'll have 2x equals u plus v, and then you get x equals 1/2 times u plus v. Kind of looks familiar. Over here, then you could go y equals u minus y minus v. 2y equals u minus, and I feel like there's an easier way to do this. It's just I'm like an idiot and I can't figure it out, you know. So anybody figures out a shortcut method, let me know. So anyways, there's that. And so you have your Jacobian is going to be then 1/2, 1/2 as usual, 1/2, negative 1/2, and then you'll have negative 1/4 minus 1/4 equals negative 2/4, which is negative 1/2. And of course, when we put it into our formula, we'll have to take the positive of that. So what the heck was the integrand? X plus y e to the negative. So x plus y times e to the negative e to the x minus y. Was that really it? I guess. So it's going to be a lot similar to this guy up here. It's probably the same problem. It's going out of my way. So, okay, whatever. So here I go at the double integral of that thing. X plus y, of course, we said was u, and then x minus y is v du. I guess dv du is kind of the traditional dv du. And my bounds are my, I need my Jacobian, so let's put that in front. The maybe if we do it in the other order, we won't have to go by parts. So let's try dv du. And so u is going from 4 to 8, and then v is going from 0 to 4. Okay, so I got 1/2 integral. The integral of u e to the v with respect to v is u e to the v from 0 to 4. Yes, that works out much nicer. And then I have 1/2 integral of u times e to the 4th minus e to the 0, which is 1. And you see that's just a big constant. So yeah, it's easier to do it that way. So 1/2, pull out the e to the 4th minus 1. You get the integral of u du. So that'll be 1/4 e to the 4th minus 1 u squared from 4 to 8. And then that'll be 1/4 e to the 4th minus 1 times 64 minus 16, whatever the heck that is. Really, I got to go and do longhand arithmetic to figure this out. 8/4 48 divided by 4 is 12, so I get 12 e to the fourth minus 1. Sorry I made so many mistakes in this video. If it's any consolation, I blame the administrators. Need to produce an army of people that are against administrators. No, I'm just kidding. I grew up in education. Both my parents were teachers, so from a very young age I learned that the administration was evil. It's not true though. Okay, so that was the answer. All right, so let's cut the video short there. Thank you for watching as usual, and I'll see you next time.